Thank you for inviting me. I've worked in the area quite a bit since 1966. I do equal parts of research in the Grand Canyon and here as well, since I finished my undergraduate work at Cornell. But this is one of my favorite parts of the country, and I helped produce the state map that shows all the glacial deposits, and there's a copy up here on the table if you'd like to see. It's available from the state in Albany, from the State Museum. But what I'm going to organize my talk around today is basically first start out with a little bit of local history and things that some of you may know about, then get into the glacial concepts and try to dispel some of the ideas that I hear bandied about ever since I've come here. And then how we function today compared to how it might have been 30, 40 years ago. And what we've learned since the 1980s, which is quite a bit actually. But people always ask, I guess today, are scientists really telling them the truth? How do we know what we know? So anyway, feel free to interrupt me anytime if I go too fast and get people lost, or you have a question that needs answering right away. I thought the first person to mention is Fairchild, who was at the University of Rochester, as you may know. He did the early glacial studies of New York and worked out where all the glacial moraines were in the different lakes. I know he was affiliated in some way with the health facility that's been abandoned up on the hill. I forget the name. You know what I mean, though. One of the other famous people here, well, before I leave Fairchild, he also was among the founding group of the Geological Society of America. That's the organization that virtually all geologists belong to, and it was founded back here in the 1980s. And also with James Hall, the first state geologist. And as you can see, there are 3 people from Cornell, so lots of local people from this part of the world were involved in that organization. Of course, New York was kind of the frontier in those days anyway. The other person that I'm told still has relations in the area, or at least in the 1960s, was G.K. Gilbert. He did a lot of the studies in the West, involved with the Geological Survey. I don't know if the other slides are going to cut off the top, but whether we need to move that down a little bit. Anyway, after I first came here, a young man came to my office and said his last name was Gilbert, and he had family in the area. Does anyone know Gilberts in the area? So, into the real topic. Now, if you'll notice here, these are the ice sheets that existed back 100,000 years ago. And the main point is the glaciers weren't centered at the North Pole. There's ocean there, and you can't have a glacier where you have ocean. It can only form on land. So we have the various ice sheets, including our Laurentide ice sheet. But if you notice, if you were living up here in Canada at the time, of course you couldn't live under the ice, but if you were up here, the ice would be coming at you from the south, not from the north. So we think of the glaciers coming from the north, but it really depends on where you were at that time. So Hudson's Bay was kind of the center of where the activity was thickest. But until about the 1980s, yes. Okay. Can we turn the mic up? Or if you were taking geology in the 1980s, you probably would have seen in books figures like this, which indicate there are only 4 glacial things that we knew about, and those are the names over on the side. The most recent being the Wisconsin. That term is still in vogue, and also the Illinoisan, but the other terms are no longer used, and it's a lot more complicated than we thought. So this old concept is in the old textbooks, but it's a lot more complicated. And if anyone asked you, or you wanted to think about where the ice was, the ice basically was north of the Missouri and Ohio rivers. So if you can picture that on a map, that gives you the basic area that was under the glaciers at different times, but many times. And often you hear it described as glacial drift. That term is because back then, in the middle of the 18th century, or the 1800s, it was largely thought that the only way you could get glacial deposits would be to have icebergs floating across the continents. And that would account for all these rocks we see, as they couldn't think of any other way to explain it. And until Louis Agassiz came over from France and explained the geology of the Alps and got people to start thinking about major glaciers. So they were pretty thick, close to 2 miles in the middle, but they weren't that thick in this area. That's another misunderstanding I think people have. Those are the contours showing where the thickest areas were, and notice there were 2 centers, one here and one here. Now, we know how thick the ice is because if you look at a theoretical curve, the physicists show you this dark line and they tell you that that's how ice would behave as you pile it up thicker and thicker. And once you pile it up, once it gets thicker than a couple hundred feet, it begins to move under its own weight and plasticity. And they compared that to Antarctica and Greenland, and as you can see, the actual profile in Antarctica and Greenland is pretty close to what the theory would predict. And the other point is, in order to have a mile of ice, you'd have to be 70 miles from the front in order to have ice that thick. And if you were 280 miles back, then it could be 2 miles thick. So we were never under 2 miles of ice. And also, when you talk about when did the glacial period end, it depends on where you were. If you were down here in Long Island, it ended about 28,000 years ago, at least the last ice. But if you were up here in Canada, you were still in a glacial environment 7,000 years ago. So the results of the last glaciation are shown in red. These are all the places where the ice temporarily started. We call them end moraines, or moraines. And that shows you how the ice receded from its location here and over in Long Island and moved north over the next 28,000 years. So why do we make such a big deal about moraines? Why are they important? Well, on the East Coast, they're obviously important. Long Island is strictly a glacial deposit. It wouldn't be there if it weren't for the glaciers. And the same with these islands, Martha's Vineyard. Cape Cod is entirely made of glacial deposits, no solid rock. Just out of interest, my parents grew up across the street from this moraine known as the Charleston Moraine in Rhode Island, where I just returned last weekend, having picked up a bite by a Lyme disease tick, which did not make me pleased. But that moraine is really quite impressive. It's over 50 feet high right along Route 1. So why do we spend so much time talking about moraines? How do these things form? You really have to understand glaciation, so I'm going to take you on a quick tour. There are 3 motions the Earth undergoes. One is precession. If you played with a top, you know that after you spin it fast, it begins to slow down and it wobbles like this. That's called precession. The Earth does that, but it takes 26,000 years to make one circle. All right. Then it also tilts back and forth. It wobbles about 2 degrees, and that's called the change in inclination of the axis. And that takes, a full cycle takes 41,000 years. Then we're at different distances from the sun, and actually when we're closer, we're often actually colder. So the distance is not as important, but that's called eccentricity, and that reoccurs every 100,000 years. So the important thing about glaciers is once the northern latitudes are pointed away from the sun, that's when the glaciers form. So the Earth's axis and location is very important. And if you look at those motions, I know this is confusing, but don't be confused. This is the precession happening every roughly 26,000 years. The tilting of the axis every 41, and the eccentricity about every 100,000 years. But all this means is they're either tilted toward the sun or away from the sun. And if you put them all together, the result of all 3 curves is the one down here. So this is how much sunlight is striking the Earth over time. And it's hot up here and it's cold down here, so it gets hot and cold. And as a result, these are the periods of glaciation: 1, 2, 3, 4, and so on. So we've had many glacial periods. We knew this years ago. This was called the Milankovitch cycle, but we had no way to date it. We didn't have anything but radiocarbon dating. So when Milankovitch proposed that this was the cause of glaciers, there was no way to prove that these ages coincided. But if we stretch it out a bit, now we're just looking at the last 4 cycles. Here's today, it's warm. It was cold, and it got warm, and then cold and warm, cold and warm. And if you look at the scale for 400,000 years, there's 4 cycles. So each cycle is roughly 100,000 years. And it matches exactly the temperature change is related directly to the amount of carbon dioxide in the atmosphere, which is, of course, what we're concerned about today. But the carbon dioxide cycle matches the glacial cycle. Now, carbon dioxide, just briefly, the sun hits nitrogen in our atmosphere, which is very abundant, and it changes the nitrogen to carbon-14, which gets involved in the carbon cycle in plants. So plants absorb CO2, animals eat the plants, they both die and get buried. So we can either date animals or plants by how much carbon-14 they take. And it only lasts for 50,000 years. By that time, everything is gone and it starts all over again. But so you can't measure the age of anything more than 50,000 years. So as a result, people have been drilling ice cores all over the planet, and mainly in Greenland and Antarctica, because that contains a continuous record of all of the air from every year that it snowed on the glacier. And it traps bubbles of gas in the atmosphere, and that's how they know the carbon content and what the temperature was over time. But every once in a while, too, there's a big volcanic eruption, and you get volcanic ash, so we can use that to calibrate the carbon cycle to make sure that we're not counting the wrong number of layers in the ice. So they've drilled in 4 places in Greenland, and these are the well cores. They're over 2 miles in depth, and they have roughly 2 million years of record, which is almost the entire glacial period. But what we're interested in is what are we standing on right here? We're standing on what's called the last glaciation, the Late Wisconsin. It started roughly 28,000 years ago when Long Island was the edge of the ice. And the present is up here. And all this curve represents is the warming and cooling. Warm is up, cold is down. So you can see a glacial period is not simple. It fluctuates due to those planetary motions that I told you about. But if you'll notice, scientists wonder, why did it do this for 30,000 years, and then all of a sudden, the last 10,000, we've been lucky, and this is all that's happened? Are we going to go back to this sometime in the future, as we have in the past? And the last major thing to happen, which we finally have a record of in the Genesee Valley, is it almost warmed up here 13,000 years ago, then all of a sudden it got very cold in 13,000, and I'm going to explain that later as to why that happened, but we have a record of it here. Now, ignore the right-hand side of the diagram. This is just showing you how many periods of glaciation there were back to 2.58 million years. That's now the official boundary of the Ice Age, known as the Pleistocene. So there were 30 or more. At least 20 of them came down as far as, say, Geneseo or crossed over Lake Ontario. So it's cold on this orange side and warm on the black side. But each one of these cycles, this is 100,000 years. So this is what we call the last ice age. It's just that bar. And I'll expand that out here. This is that same cycle, only all we're looking at is the last 100,000 years. This is the so-called Wisconsin. You can see it starts about 100,000 years ago. It was warm then for maybe 10,000 years. Then it cooled a little bit, that's called the early Wisconsin. Then it cooled a little bit more, that's called the middle. And everything that we're standing on belongs here. This is the late Wisconsin. It covers maybe 28,000 years from Long Island as the ice retreated, and then it quickly got warm. So when you walk around our surface in Western New York or anywhere in New York, this is all you're walking on, these deposits. Now this is the entire Wisconsin, starting down here at 123, and this goes to here, and then over here, and then over here. So I've just showed you this part, just this little part over here. But in the Genesee Valley, we have a record going back 39,000, so that's before Long Island existed. 39,000, now we have the Long Island record we know. Then we have the valley heads here in Dansville, which is just a little less than 17,000. And then we have 13,000, which I'll talk about later. But you can see it's very complicated. It's not a simple situation. It's not just cold and warm. The gray areas are warm and the white areas are cold. That's a simple way to look at this diagram. Now, the question, were we a Finger Lake? We definitely were a Finger Lake. And the reason is there's a moraine, and it happens to be the 13,000 year moraine. Here near Fowlerville, if you know where Fowlerville Road is on the way to Avon, there's a large moraine that the ice built and blocked the Genesee River. So as the ice melted, the Genesee River tried to flow north, but it couldn't, so it filled this lake. Not for very long, because it's such a powerful river, it quickly cut through the moraine, so it probably only lasted a couple hundred years at most. But notice it was the third largest Finger Lake, basically. But it wasn't very deep. It probably wasn't any more than 100 feet deep. And since then, the Genesee River has deposited about 50 feet of sand on top of what was the lake originally. Right, so this is Livingston County with a LiDAR image. You'll see others. LiDAR is a new technique that gets rid of all the vegetation, so you can see what the land looks like under the trees. And here you can see that it's a complicated landscape. This is the flats with Dansville. And basically the Genesee River probably flowed here at one time. It also flowed from Portageville through here, through Nunde. The middle part of Letchworth is very different from the falls from the falls and the dam end, which are very narrow, and this valley's wide. There's a buried valley here that circles around the waterfall, and it goes off in this direction, but we don't really know. But the result is, this is from all those 20 glacial periods. So the ice kept coming back, and every time it melted, we probably had a slightly different result for the Genesee River. Certainly most of the time it flowed through here, but it could have easily flowed elsewhere. So those different valleys, this one shows the middle part of Letchworth Park a little better. It's much wider here than it is here and here. And the old valley comes through here, something like that. We've tried to find out where it's buried, but we haven't had much luck. However, it did deviate, and this is another misconception I've heard mentioned many times, that the Genesee River used to flow through Irondequoit Bay, and then it switched over. When the ice melted, it didn't like that course, so it went over here. Well, this is a very deep gorge. Here are the contours on the bedrock. This is a really old, deep valley. It's below sea level, and the Genesee River probably flowed this way many times in those many cycles that I showed you. And it's only the last one, when the ice abandoned the area around the Pinnacle Hills in Rochester, the river was unable to continue this course through Rush, so it simply created a new course. So this is entirely new, less than 13,000 years, and it has nothing to do with with this old valley, which was the Genesee River, maybe many times, but not recently. Now, what did the ice look like here? It wasn't a big wall of ice. It got thinner, as I showed you on that curve, as you came to the edge. There were lakes in front of it. And then often near the front there were these upland areas like the hills around Dansville, so the ice would have been just in the valleys, and it was not like this. As much as it might be interesting to think about it, it did not form a cliff that was a mile high. As it retreated, deposits formed along the edge, which we'll be talking about more. But the main thing is, any large glacier, whenever it encounters a valley like the Genesee Valley, there's always a tongue of ice coming out. So you might imagine that this is Avon up here, and this is the tongue that coming down to Dansville. And that's just the nature of the thickness of the ice. The thicker it is, the further it can flow down the valley. So at some point in time, the Genesee Valley would have looked like this. And because Lake Ontario is so low, the ice has to climb out to get to Pennsylvania. It has to go uphill by several thousand feet. And as it did that, lakes formed in front. I can't show a big lake because we don't have pictures going back that far, of course, but there were big lakes in front of the ice as it advanced, so fed by things like the Genesee River, and they were quite large. But we need to get back to how do moraines form. I think people have the idea moraines form because the ice acts like a bulldozer and just pushes the material. Well, that's really not what happens, because when you get to the front of the glacier, if the ice is less than 300 feet thick, it's brittle and it doesn't flow. In other words, it's like the ice cubes in your refrigerator. You have to move them physically, and you can't make them flow like plastic or molasses. So what happens is the ice behind it, which is moving, comes up against the brittle ice, and it forces it to go up in the air like this. So big chunks break off, and it drags the material that was originally under the ice, it drags it up like this. And that's how moraines get formed. So that stuff comes out at the front of the ice, and it dribbles down and piles up at the bottom as it melts. So when a moraine is formed, all that means is the sun is melting the ice at the same rate that it's advancing. So the ice is moving along here at a certain rate, and the sun is keeping up with that and melting it. Therefore, the front is stationary. But it's really not stationary because all this stuff is moving. But the result is, after a while, the sun wins, the ice begins to melt back, and it leaves the moraine behind. So it's not a bulldozer effect. Although, of course, now if that ice suddenly reversed and started going this way, it could conceivably, do a little damage over here. But the main way that the moraine forms, as you can see, is the dirt that's brought up in the ice and then melts. So what we have in terms of a record is we have all these records of where the glaciers appeared to stand still, but where the solar radiation balanced the melting, and that's what we're looking at. And hopefully when that happens, something gets buried, either a dead animal, a tree, whatever, something gets buried in the moraine, and that's how we get the age using radiocarbon, at least for the last 50,000 years. But this would be a typical scenario. The ice is getting thinner, the dirt is coming out, it's forming a moraine. There's an outwash plain, which is the rivers that are carrying the meltwater. And then we have proglacial lakes, which filled all the valleys in central New York at this time for roughly 17 or 18,000 years. As the ice retreated, the lakes in the Genesee Valley kept getting lower and lower, until finally only Lake Geneseo was left between here and Fowlerville. So a typical glacial view, even though this is a mountain glacier, this would be a typical view in front of any ice sheet, no matter what it was. Now, of course, many of these features are small. Here's a little glacier in Canada. It just moved a little bit a few years ago, and it formed a tiny moraine. And of course, a couple hundred years, you wouldn't even see something like that. It would be erased by erosion. But other amazing things happen. Again, you can see how the layers are bringing the dirt up to the front, but there's so much dirt, and it's so slow that in this glacier in Canada again, you actually have a mature forest growing on top of a glacier that's moving. So when the ice is gone, you end up with a moraine. This would be in Greenland or Iceland. I think it's Greenland. And it shows you what's left behind when the ice is gone. The glacial till is out here. And you get topography that looks like this, just like you see around Dansville between Naples and Portageville. And of course, if you could see the bedrock, it usually tells you which way the ice was moving. Glacial till is unique. You can always identify glacial till because it's a mixture of everything from clay to silt to sand to stones. The stones have scratches on them, just like the scratches on the bedrock. And the only thing that could possibly be related would be a landslide. Sometimes landslide deposits look, but landslides are small. Glaciers are huge. So in the front of any glacier, you get esker features that I'll cover in a minute. You get drumlins, you get moraines, you get little lakes forming. Those are the typical things we look for to prove it was a glacial region. Drumlins in New York are famous, as you may know. Driving along the thruway from Rochester to Syracuse is the most famous drumlin area in the world. Drumlins always have their steep face facing the glacier, and then this is down glacier, south. On the topographic maps, they don't stand out as much, but this is, again, a LiDAR view that strips away the trees. This is the area somewhere between Rochester and Syracuse, where if you drive on routes 5 and 20, you're constantly going up and down over these hills.
Can you tell us where a specific drumlin is located in the Rochester or Syracuse area?
Well, anytime you drive on Route 390 and you look off to the sides, if you see a hill shaped like that, it's a drumlin. They're best seen just in the area about Avon North. It's probably easier on the east side of the road. But generally, the environment in front of the glacier is very complicated, like this one, in a modern glacier. So when all that stuff is gone, you end up with little ponds and hills. The hills are called kames, and the lakes are called kettles. So you end up with kame and kettle topography, like you see here, and with little kettle lakes here and there. Eskers are another feature. Sorry?
Maybe everybody else understands this, but drumlins run north-south, right?
Right, they run in the direction the ice was moving.
But wouldn't the moraines be east-west?
Sorry?
Would the moraines then be north-south, or would they be east-west?
No, they're east-west because they form along the front of the ice. So the ice is moving this way, but the shape of the ice is this way. So that's the east-west, and this would be the north-south.
And how, I can't quite understand how drumlins would form.
Well, the drumlins form under the ice as it moves over the area. It's a study that's somewhat controversial, or a theory, and sometimes drumlins are obviously formed by the glacier moving over them. Other times it's not so obvious. There's a whole history of literature, and it would take another lecture to explain why it's so complicated. But basically they're formed under the glacier, and they're formed near the edge. They don't form way back in the middle, like 100 miles back. They form right near the edge, probably in the first 20 miles under the ice, because it has to be relatively thin.
So the moraines would be higher than drumlins?
Moraines can be higher, but the drumlins around here are often 200 feet high. Then we have the tunnels where the streams are trying to get out that were melting, and the water had to go somewhere. Sometimes they cut tunnels through the ice, esker tunnels, and then the eskers fill up with sand and gravel. This is kind of a model similar to Mendon Ponds. If you've been to Mendon Ponds, there are two eskers right next to each other. Much like this would be the scenario, and I have a map up here of the geology of Mendon Ponds if you wish to look later. Right, till often looks brown at the surface because it gets oxidized by weathering and soil formation, and then it often gets darker as you go down. We have glacial erratics. It can move big boulders, even house size. But the most famous moraine in New York, for whatever reason, is the Valley Heads Moraine. It's called that because it forms in the southern edges of all the Finger Lake valleys, and including Dansville, which would be here. And one of the misleading ideas that I hear people say is that the reason for the Finger Lakes is they were dammed up by these deposits. But the deposits are here because the land rises. There's more sandstone in this area, like around Dansville. And the ice had more trouble eroding the sandstone. So the land rises over 1,000 feet as you go from Dansville up to, say, past Stony Brook. You have to climb about 1,000 feet. That's because these rocks are hard, and that's the only reason the moraine is here. It really has nothing to do with, or not directly due to the reason for the Finger Lakes. So that famous moraine we now know is just under 17,000 years old. It's dated over here near east of Syracuse by a geologist who works in New England, and he found material to date it in that location, but we have no dates specifically in this area. This is a shot of the moraine here, looking a lot like those cartoons that I showed you. You know, Cayman Kettle topography, irregular. It's quite wide. If you drive up the hill from Stony Brook Park up onto the higher area, that whole thing is a moraine all the way up that hill. You're driving on a moraine. That's how big it is. It's one of the biggest moraines in the area. So that would be here. You're going from Dansville up through Stony Brook. At one point, the edge of the ice was right here. In fact, there's a road here that's called Moraine Road. Maybe some of you know that. And at that time, this was the ice. And meltwater was escaping from the Swains Valley, coming this way, and off the ice going this way. So there was a huge amount of water headed towards Binghamton, and that accounts for all the gravel pits you pass on the way to Binghamton, because there were huge torrents of water at different times that created all the sand and gravel. But it's a little more complicated. When this existed, part of the ice was trying to go toward Wayland over here. So at 19 or close to 17,000, this is the topographic map. These are the ones that I just showed you, Moraine Road here in another position. But it was also headed in this direction, so there are two ridges as you follow the road to Naples. Just before you get up onto the flat, there's a ridge here that's about 20 feet high, and another ridge here just past the road that goes up to the reservoir. And if you look carefully, you can see the ridge. It's obvious on the map. If there's corn growing, it's not so easy to see because they're not big features. But the point is, because there's a big hill here, the ice split and flowed in two directions. And it gets more complicated. All right, so this is a blow up of that. Here's that ridge. It's only a couple of contour lines. But notice the ice was coming down and then it was actually going this way. It actually turned around, at least a piece of it, and it was flowing toward the reservoir. And as you drive up the road here, you can look across and see this part of the moraine. And there's a new house on this road, but this was the old channel where the meltwater came out. And then there's another ridge, which is very hard to see. But it went through Wayland and got almost to the Canandaigua Lake Valley. And then the two lobes met each other, the Genesee Valley ice coming this way and the Canandaigua Valley ice coming this way. They met in the middle and formed what's called an interlobate moraine because it's formed by two glaciers going in opposite directions. And the meltwater was trapped. It couldn't get out through the hills. So a small lake formed and it raised its level till it found Black Creek. And the reason Black Creek is so steep is because the melting water from the lake eroded this channel. So that's kind of a neat feature. And you can see further down Canandaigua was the actual front of the ice. So if you look at that someday, if you're driving to Naples, you come up out of the valley and you go over a high area and back down again. And right in here you can see lots of cames and kettles, which are these little round circles where the ice blocks were melting. And then this is the lake outlet for Black Creek. All right, so features like that, which because the soil is so sandy around here, often our kettles don't end up filled with water. So what was the history overall? If we go back to Long Island at 28,000, it took 15,000 years for the ice to melt and get back to the Canadian border. But you can see all the major valleys had these ice tongues, like the Hudson Valley and the Connecticut Valley. And that's why the ice front was not straight. This is the glacial map of New York. It comes in 4 sheets. It's for sale by Albany. Dansville is just, and the Genesee Valley are just on the edge. Then there's another sheet that goes over to Niagara Falls. But we produced that in the 1980s and 90s. But it's not the detail that I'm giving you, but you can see all the moraines are in red and purple. So the other part of the story is the lakes that formed. You can imagine that Dansville might have looked something like this. We didn't have mountains, but you had pretty good hills around here. So each time the ice advanced, there would be a lake. And they're very useful to geologists because when the ice retreats, the water drains out of the lake and it leaves 2 things, a shoreline and all this clay and silt. And we can trace those across the landscape. So there were several lakes in the Genesee Valley as the ice retreated. And where the lakes were the largest, they created nice beaches, and those beaches were utilized, after the ice melted. Before the trees started growing again, probably a lot of the area would have looked like this. This is in Canada. And the result is a lot of these old cobblestone houses and buildings are made, and they follow along those shorelines where there were plenty of stones that were all about the same size. So that's one of the reasons they're there. In some places it's really obvious, like this Canadian view where the lake is gradually decreasing in elevation. And you can see the old shorelines today, and they're very young. But if you go back, you can go to somewhere like Montana and see the same features, shorelines that indicate where the lakes were back at that time. So as the ice is advancing, it's always going to be in water, at least in this part of the world. So you have the glacial till forming under the ice, then some of it is dragged up and ends up as silt and clay in the lake, and then stones fall off the glacier, and they're called drop stones, and I'll show you an example. The lakes were quite large, like this one, called Lake Whittlesey, and so you can follow today the old shoreline and find these kinds of features, and that's often how we put together the landscapes that existed. One thing that most people don't know about Lake Ontario, for a long time, Lake Ontario had no outlet. It didn't have an outlet to the ocean, and it shrank down so that it was much lower than it is today. And the reason is the ice depressed the Earth's crust. It pushed the crust of the Earth down over 2,000 feet in the area of Hudson's Bay. So as a result, this area was lower and this area was higher. So instead of the water going into the other Great Lakes, the water made a shortcut from Lake Huron and cut across through the Ottawa River, and the ocean came into this location, and then the freshwater melting freshwater met the ocean here on the Canadian side in the Gulf of St. Lawrence. So then we had to wait a while for the land to get, once the ice melted, we had to wait for the land to rise, and that would slowly push the outlet from here back to here. So when the ice was melting, it was pretty messy, but there were certain things that happened then. And one of them is meltwater is trying to escape from the glacier, and as it comes out from the glacier under pressure, you can have features like this forming. And this is an important part of the story later. So here's a moraine that you can see the ice peeking through here, and meltwater under pressure being forced out from under the ice. And because it's very cold, it can actually be below freezing. The freezing point, it will actually freeze instantly once it comes out under those conditions. And the way we identify those things in the field, if you go into gravel pits, I've seen several of these where you can see the layering of the sediment was horizontal, but when those things form, it forces the sand up and destroys the layers, and that's how we know those things have formed. The other bit of history we've learned due to the collapse of the salt mine in the 1990s is we were able to drill all these holes down the valley to Saunier. So we have a much better idea of what's going on, including this moraine at 13,000, which I'll come back to. But this is the picture we get from these wells, so sometimes when something bad happens, you get nice data. But in this case, this is the deposit that would represent what happened when the Valley Heads moraine formed. Dansville would be over here a little further. This is approximately Saunier. So at around 1609, that formed. Later, this moraine formed, and it didn't go as far. It didn't quite make it to Geneseo. So the Valley Heads here, then 13,000, around Valley Heads time, we had 1609. Then the Genesee River came in and deposited sediment. But below that, we have things that we don't even know how old they are, but it's part of that scheme I showed you in the beginning with all those glaciations. This belongs to a much older period. We just have no way of dating it. You asked about drumlins. Here's the drumlin field south of Rochester in Monroe County. You can see there's lots of them. There's a lot fewer down here in Livingston County. But the moraines that I just talked about, you can barely see. If you look carefully right in here, there's moraine. The other famous moraine, is Pinnacle Hills, which is here, with all the radio towers in Rochester. The U of R is on the other side. Come back to that. But this goes back to the middle of Wisconsin, not the last ice age, but the middle part. And for location here, this is West River Road, where it makes the big bend before you get to Scottsville, and there are lots of sand and gravel pits if you have traveled that route. I think there's now a transfer station here where I was collecting this information about 2000. What we find here is first of all, we see old Genesee River sand, but we have wood in it, and it's this old. Then we had a glacial advance and a lake forming this, and then it melted, and we got the sand and gravel. And if you look at this closely, here's the Genesee River gravel close up. Here's when the lake formed, and notice that the lake deposits actually preserved the stones on the floor of the valley as it formed, and then the ice came into the lake. Now, how do we know the ice came into the lake? Well, the lake has layers in it, layers of silt and mud, and they got messed up like this. So obviously the ice pushed its way into the lake. And we call those features glacial varves. They're about an inch or so thick, and in the summer they're this color, and in the winter they're darker. And the reason is in the summer the lakes aren't frozen, so there's a lot of activity and storms and so on. And then in the winter everything freezes over and all the plant life in the lake dies. So we're able to get radiocarbon dates from these dark layers, and we can actually date each layer as the lake formed. The iceberg stones that I mentioned, they fall into the lake, and you can see the layers under the stone are nice and horizontal, but once the stone fell, then the layers have to take into account the fact that the stone is present. So that's a good way to identify a glacial lake environment. So those stones dropping into the mud. Now, a bigger view of that gravel pit I showed you there are two glacial tills. One on top of the Genesee River gravel, then a melting of the ice, and then it came back. So we have a glacial till here and a glacial till here. But they're roughly the same age, less than 100 or 200 years apart. And the reason we're able to date it accurately is here's the Genesee River gravel. The first layer on the lake, notice how black it is. That's because the formation of the lake killed all the organic material that the Genesee River was bringing north. So we got a good date here of roughly 35,000. And then the ice came in after that. So some of the terms on these slides are for different lectures, so don't worry if I don't mention every word. But in addition, when we looked at the Genesee River sand, we found the roots of plants, and we could also date those. They were a little older, of course, around 41,000 for the youngest wood that was underneath, and this is when the lake formed. We have to correct the radiocarbon age, but when we correct it, it changes it from about 34 to 38. And that's another story, but we now know how to correct the ages. And this is how fresh that wood looks that's buried in the material. It looks like something you could find, if you went digging in a swamp today, you'd find something like this. So 28,000 at Long Island, 16,900 here in Dansville, and at some point the ice cleared Lake Ontario, and we used to think this was the simple story, and now we know it's not quite so simple. And this is the reason. Now we're looking again at the last 15,000 years only. And remember, white is ice, gray is warm. So there's a period of time that's in Europe is called the Bowling Alroyd period, and forests grew. The same thing happened in North America. Trees came back into the valley, and then all of a sudden it got cold, and that's called the Younger Dryas. The Dryas is a plant that grows in the tundra regions today, and then it got warm. So we're living here. So why did it suddenly get cold? We were almost out of the glacial age, and something happened, and that's the part of the story that I'm going to finish up with. But it's easy to find where glaciers have advanced and retreated if you know what you're looking for. Here we have, for example, deposits in a lake, but the ice came along and messed it all up, and then it melted. And you can tell the ice was close because the layers are sloping like this, indicating, the ice was up here somewhere. So the last thing that we thought happened for years is Lake Iroquois formed. Lake Iroquois formed because the valley, the St. Lawrence Valley, was blocked by ice. There was a lake in Lake Champlain. It was much bigger, and it flowed into the Atlantic. And the level of Lake Iroquois is controlled by the rocks at Little Falls on the Thruway. And you may know at Little Falls there are some interesting rocks exposed. And that was a waterfall, and that's why the lake formed the shoreline. And the shoreline is known as Ridge Road today, as you may know. So the ice was sitting out here somewhere, and Lake Iroquois formed, headed past Utica, and Ridge Road now follows this because it was a nice level surface, and it was made of sand. So it was an old Indian trail as well as a highway. But this is the time I was talking about where, because the ice was so thick, Lake Ontario shrank and the water started going this way through the Ottawa River because the continent was pushed down by a couple thousand feet. So there were no connecting Great Lakes. There was no Niagara Falls, for example, because there wasn't any water coming through Lake Erie. All right, now what's happened since then, and we know this from looking at the lake shorelines, we see how much they've been deformed. They've risen 600 meters, or 2,000 feet up here, near the Canadian lake. And down here, if you look just at Lake Ontario, the difference across from the east end to Buffalo, roughly 230 feet. So any shoreline that formed at that time would be 230 feet higher at Buffalo than it was at the other end of the lake. So that's one of the things geologists use to figure out why the Earth is not at the same elevation. So for a while, it used this old route. Then eventually it switched to the new route. Niagara Falls formed. But at that time, the lake was much lower than it is today, and it had to rise up to that elevation before this could happen. So about 12 or 13,000 years ago, this is the modern shoreline. This is where the lake was. And I know this is a busy diagram, but all these numbers are just radiocarbon dates and things. When the ice was here, the lake dropped precipitously, 440 feet. And today it's risen, and now we're up here. So after the ice melted, because the Earth's crust was pushed down and deformed, the lake was way down here and much smaller. But Ridge Road, of course, before it was paved, it looked like this on the Monroe County area. And here it is here. This, you can still see it on a LiDAR image. That is Ridge Road, the edge of Lake Iroquois. And I think this is the Pinnacle Hills Moraine, the University of Rochester, and lots of drumlins down here. So you can see the ice wasn't moving exactly north-south. It was kind of curved over here towards the Genesee Valley. And of course, Pinnacle Hills, here, the Pinnacle Hills, back in the old days, and a more modern view. So how do we get this other moraine? The problem is Lake Iroquois is too old, and the moraine we now find down here at 13,000 is too young, but we have good information. We have trees along the river that I'll show you in a minute. We have a mastodon skeleton, we have a peccary, an animal skeleton here, and we have a pond layer with wood in it, and all of those say that this is 13,000 years ago. So how could we have a moraine when the ice supposedly had already melted and Lake Iroquois had formed? Nobody ever knew the age of these materials, but I'm going to talk about this area which I just showed you, and then later a little bit about the area south of Buffalo. But these are the ages. The red dots are where I have ages in the Genesee Valley, and these two are over near Buffalo. And the Valley Heads Moraine is in green here. So if we look at the history, here's the evidence. As you go north from Geneseo down here at the bottom towards Fowlerville Road and Route 20 up here at Avon, we have a mastodon skeleton here, a lake here, a peccary here, and river deposits with trees knocked down by the ice, and they all give us the same age. And here are the moraines. They're small, but they're all bunched up together. And if you know where Houston Road is approximately here. So if we look at the Genesee River first, we've got the glacial till, then the trees were knocked down, then a swamp formed, and then a lake here. And they all give us ages of 13,000. I took many ages here because I couldn't believe what I was finding. But here are all these 13,000 year ages on the wood, and a little bit younger on the lake deposits, around 12,000. So there definitely was ice coming back. The peccary site is over here near Linwood, New York. And you can see the moraines. I had to outline them here because they're not obvious. But notice also the modern streams conform to the moraines because they didn't really have any choice. This is where the animal was found, in this gravel pit. And this is how it looked the day I was there on the first occasion. You can see the sediment is sloping like the glacier wasn't too far away. And the animal was buried over here. This is the hole where the animal came from, and on top is glacial till. So clearly, after the animal lived, the glacier came back, and the animal is 13,000. So using a 12-foot ladder, I collected some of the bones. And when I drew a sketch, this is a sketch of this area. At the time, I noticed the layers were continuous except in this yellow area. So this is one of those areas where the water was forced up under pressure and it destroyed all of the layers. And this is an actual picture taken right here of the fact that the layers were destroyed by the water moving upward and the bones were found here. So I suspect what happened was the animal walked into quicksand and didn't realize. I mean, it wasn't as obvious as those fountains I showed you, but it was unstable and some kind of upward water flow. In other words, not quite obvious like this, because no animal would walk into that. But this is a modern peccary, which is related to those. A skeleton from Chicago, and this is the skull of the animal around the time it was collected. Another thing interesting, it's not a very old animal, but it was in a fight already because it has a wound in the bone here. And if you turn it over, the first year, the second molars are coming in here, and the second tusks are coming out, pushing out the original tusks. And in modern species, that means the animal was probably in this range of age. So it used to be thought peccaries would only exist in the warm periods, but obviously they had to be near the ice. Probably something like this where you had some kind of sand boils or quicksand and the animal fell into the quicksand. So quicksand is another thing people are mistaken about. Quicksand does not suck you in. Because the water is moving slowly upwards, the sand grains get separated, so there's nothing to support you. And when you stand on it, you just sink into it. So it's a sinking phenomenon, like you see this demonstration. But in the modern day, what would you see? Never give up your cell phone. Okay, so now we switch from the evidence here, and this is where the peccary was. We go over to Buffalo, and we went to a farmer, and we told him what we were doing, and he said, oh, I know, I can dig you up some trees. So he took his backhoe, and he went over, dug this trench, and sure enough, we got into glacial till. And right in the glacial till were huge numbers of trees that had been knocked down by the ice. And again, 13,000. You know, just one tree after another lined up. And they didn't have any branches or roots or bark, so obviously they had been scoured by the ice and broken up into pieces. And we got down to about 10 feet, and we were still in busted up trees. So in the Genesee Valley, that moraine is here. Over where we're looking, the moraine is much further south because of the landscape. In fact, notice it's south of the Valley Heads moraine, and the Valley Heads is supposed to be 16.9, but here I'm getting dates of 13, so something doesn't match. So what might we expect? Well, the ice went into a forest. The forest was that warm period that I mentioned earlier, the Bowling Alaroid. So probably something like this, but what's missing is the lake. This would have to be happening with a lake out here in front of the ice. So we're going from this time when trees were growing to this time when the ice came back. And that formed this moraine. Just north of Geneseo is down here. So what probably happened then? Something like this. We had a forest on the upland areas. The ice came back down the valley. It formed a lake. You know, and that was the kind of environment, and eventually the moraine formed. But then you get the question, well, if that's true, what about all these older moraines? How did they survive if the ice came back? Well, the only way to do it is to call on a floating ice shelf. So you've got, in other words, you've got 13 moraines roughly from here north, but the ice came back to here. So what's going on here? Well, one way to do that, and we know this happens in other parts of the world, if the ice is thin enough and the lake is deep enough, what happens is the ice floats across a lot of the landscape, and you don't end up with destroying the original landscape. It's still somewhat preserved. The mastodon was collected in 1991. In the winter, in January, we had 2 days because they were working on the golf course that's on the road from Geneseo to Avon, and it's now in the museum in Rochester. But basically, it would have been, oops, going backwards. The other thing we found in the spring when we came back, when the weather was warmer, that the mastodon was covered with sand dunes. Well, how do sand dunes fit into a glacial environment? Well, it's not actually hard to believe. If you're near a modern glacier like in Antarctica or Greenland, you get amazing winds called adiabatic winds that come off the ice because the air is cold and dense. And when I was in New Zealand, I experienced one of these on a glacial valley, and it was a real dust storm. So presumably that happens because there's nothing to hold the vegetation. There's no trees or whatever. And furthermore, this is the area on West River Road, north of Avon. If any of you remember where Sterling Homex was, this is in that area. These are sand dunes on West River Road, just north of Avon, and I guess it's still in Livingston County. So we had students dig into those and demonstrate they really were sand dunes. So before the vegetation gets reestablished, the wind obviously is important. So getting back to our story, we're dealing with this period where all of a sudden it got cold at 13,000. And why was that? Well, there's another part to the story where I'll finish up, and that is events that have been called Heinrich events by the person who discovered them. They are sand layers in the ocean, and there are several of them. What happens is the glaciers really start moving and they produce a lot of icebergs. The icebergs go out into the ocean, they melt, and sand layers form down here. And during those events, there are only a few, but the floating icebergs are full of material like that. And what they do is they collect the sand and also the fossil shells, and that gives the carbon date, radiocarbon date on the age of the sand. And here's what they are. They're called H0 through H6. And they can't go back any further because we're running out of 50,000-year-old ages for radiocarbon. But it turns out that many of these are the same age as the moraines. Now, some of these I haven't corrected all the ages for the radiocarbon, but this would be Long Island, right? So if you look at this diagram, all of the red arrows are places where those events in the ocean match the ones on land. So you can see the 39,000 from near Scottsville, the 28,000 at Long Island, the 16,900 at Dansville, and the 13. So one of the concerns today is, what's going on in the ocean? Whatever happens on land, similar things cause disturbances in the ocean. And one reason geologists think it got really cold at 13,000 was so much ice was melting. It was suddenly being flushed into the North Atlantic. And a big, around that time, after the outlet was formed for the Great Lakes, we have something called Lake Agassiz, which is the biggest lake that ever formed from the melting ice. It wasn't very deep, but its outflow was along the St. Lawrence and also through Hudson's Bay. And that dumped all this cold water into the Atlantic Ocean along that route. And what it did was it messed up this major circulation pattern. Now, this was in the news last week that scientists are now concerned that we're going to mess this up again. This is a 2,000-year cycle. The warm water is heated in the tropics. It comes up past the British Isles. Some places in Scotland, they actually can grow subtropical vegetation. And of course, it's part of the jet stream over here. But then it cools off and it goes back down and then it comes up again. But it takes 2,000 years for that cycle. And with global warming, people are wondering, you know, if we warm up the Atlantic, we're not talking about glaciers now, but if we warm up the Atlantic, is that going to mess up the cycle and change the climate in Europe and North America? So, is there a clue we can learn from this event that happened back then, even though it was a glacial event? You don't want to mess with the North Atlantic current. Stay tuned. The end. Any questions?
Sure, I have a question.
Yes.
We talked a little bit about this, but for those of us here, what are some of the main glaciation or geological differences between the Finger Lakes and the Genesee Valley?
Not really a lot of difference. It's just that they have lakes so that you can't see what's under the lakes. And some of them are below sea level. They were eroded actually below sea level because the ice was so thick in that area. But, you know, the moraines cross. If you follow routes 5 and 20, you can see a lot of the moraines that show on the map up here. Yes?
Couple things. Just to put things in perspective, you know, one of the main geological features that people know about are the salt deposits. Now, I know you have to go a lot farther back in time for those. How far back?
Well, that's the Silurian, which is, you know, most of the rocks on the surface of this area, Devonian, which is roughly 400 million. The Silurian is the next geologic period under that. So the salt is down there, and of course it goes from roughly Albany to Chicago.
Also, what was going on with the Genesee River while the glaciers were going back and forth? Was it still trying to flow north, and if so, where did the water go?
Well, of course, when the ice was at the Pennsylvania border, there was no Genesee River, but it kept growing as the ice retreated, and it kept getting bigger and creating lakes. So there were, I think, 15 lakes by the time it got from Pennsylvania to Rochester. 15 different lakes formed. Many of them covered large areas. But the last one to form was Lake Geneseo, and then the water went out through Syracuse.
And one last question. Again, to put things in time perspective, what's the oldest evidence of human habitation in upstate New York?
Yeah, there's no good record from New York, but I understand there's somewhere maybe close to 16,000 in Pennsylvania in a cave, and they've been finding similar things in Mexico, so I think they're beginning to push, you know, the settlement of the North American continent back further, but I'm not exactly sure on the current age, but I know there's not a lot of evidence in New York.
So maybe that peccary was running away from someone.
Yeah, exactly, right. It could have been hunted. And it stands to reason various cultures would follow the rivers for the environment and the food supply. But did you have another question before?
Oh, I'm sorry. Does the theory still stand, speaking of myth busting, that the actual glacial ice flowed into and scooped out the Finger Lakes?
Yes, it scooped out the Finger Lakes. But one of the interesting aspects of that question is when we go to my site up near Scottsville, when the ice came all the way down, it didn't destroy, I mean, the younger ice that made it to Long Island did not destroy the deposits at Scottsville, which are only 20 feet below the surface. So I think in some cases, it depended on how fast the ice was moving and whether it was going into water, which might have acted as a lubricant. So I think it's a more complicated story. And we don't really know the history of all the Finger Lakes.
Any other questions? Why isn't the Genesee Valley a lake?
Because there's so much water in the Genesee River, it cut through the moraine right away within 100 years or so. So it just keeps cutting down and prevents it from being a lake.
So the north end let the water out.
Exactly right. It probably lasted for 100 years or so, because it's a pretty strong erosional force with that amount of water, and the moraine is not that hard to erode. And none of the other Finger Lakes have big rivers coming in from the south end. Yes?
I've long been confused about cams. Could you explain what they are and how you might recognize them if you're driving across the landscape?
Right, well, cames is a general term that people use for almost any little hill. If it's not a drumlin, it's kind of round shaped. And in Europe, it's considered that it should be formed by melting water, and it should be mostly sand and gravel and not glacial till. But you know, when you look at the shape of it, unless you dig a hole in it, you really can't tell what it's made out of. So I'm sure there are things that are called cames that may not be the British equivalent of a came. But essentially, when the ice is melting and it gets very irregular, some parts fill up with sand, and then when the ice melts, they end up being a hill.
So would that be the same as treated moraine?
As what?
Would that be the same as treated moraine?
Beaded, did you say?
Pitted.
Oh, pitted, yes. Pitted would refer to the fact that you have lots of cames and kettles together so that you get ups and downs. Another question we had over there.
That river fork, that river bottom, is that caught by the Genesee River?
Yes, and only I'm sorry, you said the Genesee or the?
No, the Letchworth.
Letchworth, right. Yes, that was cut. Obviously, if the ice was here at 13,000, it had to be cut after that.
Same with the Rochester Canyon?
Yeah, the Canyon Rochester, less than 13.
So is that why the flats are always wet?
Well, it's
Always wet?
It's partly, but it's also because the Genesee River carries a lot of sediment and it builds up the floodplain near Mount Morris, and the Canaseraga can't keep up with it. So in big floods, the Canaseraga actually flows backwards, flows towards Dansville. So I think over time, the Genesee and the Canaseraga are competing, and the Genesee's winning. So you have nice soil and stuff back in the flats. Well, as I appreciate the invitation, but also I have one book that Dick Hathaway, the former mayor of Geneseo, and I wrote back in the 80s, and this covers all the topographic maps. It starts out in Brockport, and it goes around the Genesee Valley, up Honeoye Lake, and around routes 5 and 20. So if anyone ever wanted to take a Sunday drive, I only have one copy, it's out of print, but if anybody wanted to make color copies of this, I'd be glad to loan it, and you could take a Sunday drive. It shows all the features I've mentioned are marked and labeled. So if you're interested, or also to look at the map of the state of New York.